Titration is a lab technique where we are performing a controlled neutralization reaction. We are reacting an acid with a base. We can calculate the pH at various points of a neutralization reaction once we know whether we have a strong acid or a strong base. Now, when we have a strong acid or a strong base, this is purely a neutralization reaction. If we're going to calculate the pH, we have to know what is in greater quantity, concentration of the hydronium or the hydroxide. Now here, we're given the example of hydrochloric acid reacting with sodium hydroxide. That reacts to form water and our salt, sodium chloride. So when we have a titration that's carried out with 25 milliliters of a 0.1 molar hydrochloric acid, and then we will be adding strong base, so sodium hydroxide, to it, and that sodium hydroxide has a concentration of 0.1 molar. We're asked to calculate the pH after specific volumes of base have been added. Now at first, we're asked to calculate that pH when no base has been added. So the pH is going to be dependent on the molarity of the acid. Remember, hydrochloric acid is a strong acid, so it completely dissociates into its protons and chloride ions. So the concentration of the hydrochloric acid is going to be the concentration of the hydrogen or the hydronium ion. pH is the negative log log of this ion. So we can calculate the pH by taking the log of 0.100 and getting a value of 1.00. That's the pH before any base has been added. Once we add base, we have to start comparing our moles. So we have to calculate moles of acid, and we'll have to calculate how many moles of base. Now, to calculate the moles of the acid, we will take the volume that we started with, our 25 milliliters. We have to convert that into liters so that we can multiply it by the molarity. 0.100, capital M molarity is moles per liter. That way my liters cancel out and I am left with moles. So here I have 0.00250 moles of acid. For my moles of base, I'm going to take the volume that I was given, so my 12.5, so 0.01250 liters. I will multiply that by the concentration that was given for the sodium hydroxide, and I have 0.00125 moles of my base. Now they are going to neutralize each other, so we will subtract the moles of the base from the moles of the acid, because that's how many moles of acid have been neutralized by the base. So I have 0.00125 moles of acid remaining. In order to find the pH, I need to have that concentration. So I'm going to take that amount of moles that are remaining and I will divide it by the total volume in liters. And at this point, the total volume, I had 25 milliliters of acid. I have 12.5 milliliters of base, for a total volume of 37.5 milliliters. So that concentration works out to be 0.0333, capital M molar, and that is the concentration of my acid. And it's acid because I had excess acid here. So now to take the pH, pH is the negative log of that concentration. It's 0.333. And that value, I get a 1.48. For the third situation, we're going to have 25 milliliters of base. Now, I already calculated my moles of acid here. I'm just going to bring that down. So my moles of acid are still the same. And now I've added 25 milliliters of my base. My base had the same concentration of my acid, so here the moles of the base are equal to the moles of the acid, 0.00250 moles of acid. Now they will neutralize one another, and we will be left with nothing, no excess. Because there is no excess, this is the equivalence point, and the pH is 7 for a strong acid and a strong base, because they have completely neutralized one another. Now in the fourth scenario, we have 37.5 milliliters of base. So I still have the same number of moles of acid. And now I need to calculate my new moles of base, and I do that the same way I did above. So I'm going to take my 37.5 milliliters and multiply it by the concentration. And I get 0.00375 moles of base. Now my base is going to be in excess, and I will have an excess of this amount of hydroxide. So I'm going to find the concentration of that. I will divide by the total volume, and there are 62.50 liters of total volume for a concentration of 0.0200. Now again, this is the concentration of my hydroxide anion. I can find the pOH to be 1.70, and then the pH, which is 14 minus the pOH, is going to be 12.30. These calculations we can perform for any volume of base added. So we can calculate and tabulate this information, and then we can form what's called the titration curve. Now here we have the titration curve on the left. We have the titration curve of a strong acid with a strong base. You have the volume of the sodium hydroxide on the bottom and the pH on the vertical. Now the equivalence point is found at the inflection point. This particular titration curve shows basically a vertical line. When you have one from your lab data, you will have an inflection point, and that's where the equivalence point lands. On the right, we have a titration curve of a weak acid with a strong base. You see that the equivalence point is also at the inflection point, but that equivalence point is slightly basic. Remember our rules from the previous topic or previous module with acids and bases, that when we neutralize a weak acid with a strong base, we end up with a slightly basic solution. And a weak base with a strong acid, we end up with a slightly acidic solution. Now the calculation for a weak acid with a strong base is a little bit more involved, but you still have the same methods. Now this particular question went a little bit out of order with 12.5, rather than stepping in order 0 to 12.5 to 25 to 37.5, they flipped these. And I'm not really sure why, but we're going to calculate it this way anyway. So again, with the calculation, but a weak acid and a strong base. So number 1, the initial pH before any sodium hydroxide has been added is just going to be to find the pH of your weak acid. Well, we have our weak acid and water, and we're going to form hydronium and our conjugate base. So that weak acid is going to be 0.100 molar. We have no hydronium and no conjugate base. We're going to shift by some value x to have our equilibrium concentrations as follows. The Ka is provided for us at 1.8 times 10 to the negative 5, and that represents the ratio of our equilibrium concentrations, our products, which in this case are represented by x's, so we have x squared divided by our reactant 0.100 minus x. I'm going to simplify here, and I'm going to solve for my x. And in this case, my x is going to be 0.00134, capital M molarity. That x value represents my hydronium ion concentration. So now I can calculate the pH, which is the negative log of this concentration, 0.00134, and I get a pH value of 2.87. So that's when no base has been added. As soon as we start adding base, we need to analyze our moles. So the moles of the acid, the weak acid, are going to be found by taking the volume of the weak acid converted into liters multiplying that by the molarity, and we get 0.002500 moles of acid. Now I need to calculate my moles of base, and this time I'm calculating moles of OH specifically. So that is going to be the volume of hydroxide multiplied by the concentration of hydroxide, and that's also going to be the same value as my moles of acid. So it looks like we're at the equivalence point here because we do not have an excess of acid or base. The difference between the weak acid and the strong acid, however, is when we create this situation where we add a strong base to that weak acid, we are forcing the creation of our conjugate base. And that's all we really need to create an equilibrium. So we are forcing the creation of our A-. So it's this many moles of A- are created, however many moles of sodium hydroxide were used to neutralize. And then we're going to divide that by the total volume. So the total volume here is 50 milliliters. And when I do that, I get a concentration of 0.05, and then fill in zeros for the significant digits, capital M molar. Now that is specifically my A-. That's going to react with water in order to create my weak acid and hydroxide ion. So I have this initial value, and I have none here. I'm going to shift this concentration by some value x, and then find the equilibrium concentrations. Now this is not a Ka expression. This is reliant on the Kb. So in order to find the Kb, we need to take the Kw and divide it by my Ka, which was given 1.8 times 10 to the negative 5. So I get a Kb value equal to 5.56 times 10 to the negative 10. Now that's going to be equal to my concentrations at equilibrium, so I'm going to use x squared over 0.05 minus x. Now I can simplify this, solve for x, and I get an x value of 5.27 times 10 to the negative 6. Now that's capital M molar, and this x value is going to be the concentration of the hydroxide ion. I can find the pOH from this value, and I get 5.28. The pH is going to be 14 minus this value, and I get 8.72. So that was finding the pH at the equivalence point for a weak acid, strong base. What about before the equivalence point? Well, I'm told to calculate after I have added 12.50 milliliters of sodium hydroxide. So we need to analyze our moles. My moles of acid are 0.0025, and I found that above by taking the volume of the acid, multiplying that by the molarity. So this is my moles of acid. My moles of base are going to be the new volume that I'm adding times the molarity, and that will give me the moles of base. Now, because I have more moles of acid than moles of base, I'm going to neutralize only this amount of acid, so I need to take the difference. And this is excess acid that is left. Now, when I have a weak acid, what I have done to neutralize that acid is I have taken this amount of moles and converted it into my conjugate base. So now this is going to be equal to moles of my conjugate base. Now I need to calculate the concentrations of both of these things. So the moles of my conjugate base, 0.00125, divided by the total volume now, which is 37.5 milliliters gives me a concentration of 0.0333 capital M molar. Now that also happens to be the concentration of my HA, purely because we had the same number of moles. Now I can use the Henderson-Hasselbalch equation, and I can calculate the pH, which is equal to pKa plus the log, the concentration of the conjugate base, over the weak acid. So the pKa here is going to be 4.74, and I'm going to add to that the log concentration of the conjugate base over the weak acid. So now I have pH is equal to 4.74. So the pH is equal to the pKa at this point. Now, it is important to note that the pH is not going to be equal to the pKa at all points before the equivalence point. It just so happened to work out with this one. Now, in the fourth set of conditions, I have 37.5 milliliters of sodium hydroxide. Again, I need to compare moles of acid to moles of base. So my moles of acid is 0.00250, and the moles of base, I'm going to take the volume, 0.0375, multiply that by 0.1, and I get 0.00350 moles of base. Now this time I'm going to have an excess of OH. Since I'm going to have an excess of OH, my pH is going to be dependent on that. So I'm going to take the moles of OH and divide it by my total volume, which is going to be 62.5 milliliters, to get the concentration of my OH as 0.0200 m. Again, that is the concentration of my OH. Now I can find the pOH to be 1.70. pH is going to be 14 minus the pOH, and I get a value of 12.30. So when you have a weak acid and a strong base, it's important to take note of how the moles of acids and bases compare. Now we use what's called an acid-base indicator in a titration reaction, and we use that indicator for a visual cue as to where we can find our equivalence point. Now usually when we choose an acid-base indicator, we're usually looking for one that has a change around where we expect our equivalence point to be. The color shift occurs as the ionization of the weak acid or weak base of the indicator shifts. So here we have an example, a table that shows the different color values and the pH that they are expected to shift. So when you can identify a weak acid and a strong base, and you can calculate where that equivalence point is supposed to be, you can figure out which of these indicators would be best for your purposes.